Welcome to our penultimate module. We've explored supervised, unsupervised, and now generative AI. But there's a third major paradigm of machine learning, reinforcement learning, RL, the science of teaching an agent to make optimal decisions through trial and error in an environment. Think back to how a child learns to ride a bicycle. They don't have labeled data, and they don't just mimic. They try, they fall, they get a scraped knee, a penalty, they adjust, they try again, and eventually they learn to balance, a reward. RL works similarly. An agent learns to perform a task by interacting with an environment and receiving rewards or penalties for its actions. The goal of the agent is to learn a policy, a strategy or mapping from states to actions that maximizes the cumulative reward over time. It's not about immediate rewards, but about long-term gain. This makes RL particularly powerful for sequential decision-making problems. Unlike supervised learning, where you provide explicit input-output pairs, in RL, the agent discovers the optimal behavior itself through exploration and exploitation. It tries different actions, observes the consequences, and updates its strategy based on the feedback it receives. This paradigm is what enabled AI to defeat human champions in complex games like Go and chess. And it's driving advancements in robotics, autonomous systems, and even financial trading. It's about learning through experience. In this lecture, we'll cover the fundamental components of an RL system and some core algorithms. Let's start with the key concepts that define the RL framework. To truly understand reinforcement learning, we need to grasp a few core concepts that define the framework within which agents learn. These are Markov Decision Processes, or MDPs, policies, and value functions. Most RL problems are formalized as Markov decision processes. An MDP provides a mathematical framework for modeling sequential decision-making in situations where outcomes are partly random and partly under the control of a decision-maker. It consists of states, S, the current situation or configuration of the environment, actions, A, the choices the agent can make in a given state, transition probability, P, the probability of moving from one state to another after taking an action, and reward function, R, the immediate reward received after taking an action in a state. A key property of an MDP is the Markov property. The future state depends only on the current state and the action taken, not on the entire history of past states and actions. This simplifies the modeling process significantly. Next, the policy. The policy is the agent's strategy or behavior. It defines how the agent chooses an action given a particular state. A policy can be deterministic, always choose one action, or stochastic, choose actions with probabilities. The goal of RL is to find the optimal policy that maximizes the cumulative reward. Finally, value functions. These are critical for guiding the agent's learning. A value function estimates how good it is for an agent to be in a particular state or to take an action in a state under a given policy. The state value function, V of S, tells us the expected total future reward starting from state S and following a given policy. The action value function, Q of S, A, also known as the Q value, tells us the expected total future reward starting from state S, taking action A, and then following a given policy. The agent uses these value functions to evaluate its decisions. By learning which states or state-action pairs lead to higher cumulative rewards, the agent can refine its policy to make better choices over time. These three concepts, MDPs for formalizing the problem, policies for defining behavior, and value functions for evaluating behavior, form the backbone of almost all reinforcement learning algorithms. Next, we'll look at a fundamental RL algorithm, Q-learning. With the core concepts of RL in mind, let's explore a fundamental and widely used algorithm, Q-learning. This algorithm helps an agent learn the optimal action value function, or Q function, which directly tells it the best action to take in any given state. Q learning is a model-free and off-policy algorithm. Model-free means it doesn't need to know how the environment works, the transition probabilities, or reward function. It learns purely from experience. Off-policy means it can learn the optimal policy while following a different exploratory policy. The core of Q learning is iteratively updating the Q values in a table, the Q table. Imagine a table where rows are states and columns are actions, and each cell stores the Q value for taking that action in that state. Initially, all values are 0 or random. When the agent takes an action, it observes the reward and the next state. It then updates the Q value for the action it just took using the Bellman equation. The update rule considers the immediate reward and the maximum Q value achievable from the next state. This means it learns not just from immediate gratification, but also from the potential future rewards. This iterative update, often done with epsilon-greedy exploration, where the agent mostly exploits its current knowledge but occasionally explores new actions, allows the Q values to converge to their optimal values over many interactions with the environment. Once the Q table is learned, the optimal policy is simply to choose the action with the highest Q value in any given state. However, Q tables only work for environments with a small, finite number of states and actions. What if your environment has millions or even infinite states, like a complex video game or a continuous control task? This is where deep Q networks come in. DQN integrates deep learning with Q learning. Instead of a Q table, a neural network is used to approximate the Q function. The input to the neural network is the state, and the output is the Q value for each possible action. The network learns to predict these Q values by minimizing the difference between its predictions and the target Q values from the Bellman equation. DQN, popularized by DeepMind's success in playing Atari games, revolutionized RL by allowing it to handle high-dimensional observations like raw pixel data from a game screen and much larger state spaces. It opened the door for RL to tackle real-world complex problems. Let's look at more applications of reinforcement learning. Reinforcement learning, with its unique ability to learn from interaction and optimize for long-term rewards, is driving innovation across a wide range of challenging domains. Let's explore some of its most compelling applications. Perhaps the most famous application is in game playing. RL agents have achieved superhuman performance in complex games like Go, AlphaGo, chess, AlphaZero, and even real-time strategy games like StarCraft 2. They learn optimal strategies through self-play, developing intuition far beyond human capabilities. In robotics, RL is crucial for teaching robots to perform complex motor tasks without explicit programming. Robots can learn to grasp objects, navigate curved environments, walk, or perform delicate manipulations through trial and error, adapting to changing conditions. Automated driving also heavily utilizes RL, especially for decision-making tasks. While perception, CV, identifies objects, RL can help a self-driving car learn optimal behaviors for merging into traffic, making turns, or choosing safe routes, considering long-term consequences. Resource management and optimization is another big area. RL can optimize energy consumption in data centers by learning to control cooling systems, manage traffic flow in smart cities, or optimize inventory in supply chains to minimize costs and maximize efficiency. In finance, RL is being explored for algorithmic trading strategies, where agents learn to buy and sell assets to maximize profit, adapting to market fluctuations. It's also used in portfolio optimization and risk management. Even in areas like personalized recommendations, beyond what we discussed with supervised learning, RL can personalize content by learning from user interactions and feedback. optimizing for long-term engagement or satisfaction rather than just immediate clicks. From mastering complex games to controlling real-world physical systems, RL is enabling AI to learn optimal sequential decision-making in highly dynamic and uncertain environments. With all these powerful AI technologies, it's crucial to also consider their ethical implications, which is our next topic. As AI becomes increasingly powerful and integrated into our lives, it's not enough to just build intelligent systems. We must also consider the profound ethical implications and strive for responsible AI. This is a critical discussion. One of the most pressing concerns is bias. AI models learn from the data they're trained on. If that data reflects societal biases, for example, historical discrimination, the AI will learn and perpetuate those biases. This can lead to unfair outcomes in areas like loan applications, hiring decisions, or even criminal justice systems, disproportionately affecting certain demographic groups. Fairness is closely related to bias. We need to ensure AI systems treat all individuals in groups equitably, avoiding discrimination. This involves scrutinizing data sources, developing bias detection and mitigation techniques, and ensuring diverse teams build AI. Transparency and explainability are also crucial. Many powerful AI models, especially deep learning networks, are often called black boxes because it's difficult to understand why they make a particular decision. For high-stakes applications like medical diagnosis or legal judgments, being able to explain an AI's reasoning is essential for trust and accountability. Privacy is another major ethical consideration. AI systems often require vast amounts of data, much of which can be personal or sensitive. Ensuring data is collected, stored, and used in a way that respects individual privacy and is compliant with regulations like GDPR is paramount. Accountability asks, who is responsible when an AI system makes a mistake or causes harm? Is it the developer, the deployer, the user, or the AI itself? Establishing clear lines of accountability for AI decisions is vital for legal and moral responsibility. Finally, we must consider the broader societal impact. Job displacement, the spread of misinformation, especially with generative AI, autonomous weapons, and the potential for misuse. Developing responsible AI guidelines and fostering interdisciplinary dialogue are key to navigating these challenges. In building responsible AI is not just about technical solutions, it requires careful consideration of human values, societal norms, and ethical principles. It's a continuous effort that involves developers, policymakers, ethicists, and the public. In our final lecture, we'll look at the future of AI. We've covered a vast landscape of AI and ML, from foundational concepts to the cutting edge of generative AI. To conclude, let's cast our gaze forward and discuss the future of AI and emerging trends. One of the most exciting trends is multimodal AI. While current models often specialize in one domain, text, images, audio, multimodal AI aims to understand and generate content across multiple modalities simultaneously. Imagine an AI that can understand an image, describe it in natural language, and then compose a piece of music inspired by its content. The pursuit of artificial general intelligence, or AGI, remains a long-term goal. Unlike narrow AI, which excels at specific tasks, AGI would possess human-like cognitive abilities, capable of learning any intellectual task that a human being can. While we're still far from true AGI, research continues to push boundaries in this direction. We'll see continued advancements in federated learning and privacy-preserving AI, allowing models to be trained on decentralized data without compromising individual privacy. This is crucial for collaborative AI development, especially in sensitive sectors like healthcare. We expect more focus on edge AI, running AI models directly on devices like smartphones or IoT devices rather than in the cloud, for faster, more private, and efficient real-time applications. The future of AI is not just about creating powerful models, but integrating them seamlessly and responsibly into every aspect of our lives. This brings us to the final module.